Okay, so we saw what a resource allocation graph is. So now if we are given the following information, the list of processes, the list of resource types, number of instances of each resource type, which processes are requesting which resources have already been allocated to which processes. If all this data is given to us, we know how to construct an RAG. So you just use circles for the processes, rectangles for the resource types, dots to indicate instances. For every request, you put a request edge from a process to the resource, and for every allocation, you put an assignment edge from the resource to the process. That's how you construct an RAG. But how is this going to tell you, or at least help you find out whether there is a deadlock or not? Now the thing is, the RAG will not always be able to give you the answer to that question, but there are some rules which have been proven. So in some cases the RAG helps. So what are these rules? So given the definition of a resource allocation graph, it can be shown that if the graph contains no cycles, then no thread in the system is deadlocked. First and foremost point, no cycles, no deadlock, irrespective of how many processes, how many resources, how many instances of which resource, none of that matters. If there is no cycle, there is no deadlock. And intuitively, I think it is easy to make sense of this, right? So if there is a cycle, it means one is waiting for another, but that has been given to someone else, and that someone else again is waiting for a resource which is with this first person. So that kind of situation is what is depicted by a cycle. I'll show an image in a minute. So if there is no cycle, it is a very straightforward situation. There is no deadlock. If there is a cycle, there may or may not be a deadlock. You cannot blindly come to the conclusion that cycle means deadlock. Why? Because if there is a cycle, if you have only one instance of each resource type, then you can 100% say there is a deadlock. If you have multiple instances, then there might not necessarily be a deadlock. So it could just be that one instance has been allocated to a process and another process is waiting for another instance. So the graph will still look circular. I'll show you examples, but it will not be a deadlock situation. So we will take a look at an example first of the same case which we've been talking about ever since we started learning about deadlocks. You have P0 and P1, two processes. You have S and Q. You have only one instance of each resource type, S and Q. Now the green edges represent the request edge. So P0 is requesting for Q, P1 is requesting for S, and the blue represents the assignment edge. S has already been given to P0, Q has already been given to P1. So here you see that there is a cycle and there is only one instance of each resource. This means you have a deadlock. So if there is no cycle, no deadlock. If there is a cycle, you check whether there is at least one resource type for which you have multiple instances. In this case, no, which means this process wants this, but this has been given here. Similarly, this process wants Q, but Q has been given here, which is what we mean by a deadlock, right? So that is what we mean when we say if there's no cycle, there's no deadlock, and if there is a cycle and every resource type has only one instance, then you have a deadlock. Now what if, let's say we had two instances of Q, S is remaining the same only, but Q we had two instances. Let's see what would happen. So we still have the same processes P0 and P1. We still have the same resources S and Q. Initially we had only one of each type, S and Q. Now we have two of each type. So we'll see. Let me draw. So the nodes are going to remain the same. I'm not going to erase them and draw them again. The edges, we'll see. Now see, the first thing that happened was P0 claimed S, right? If you remember the deadlock code we saw, P0 first claimed S, which means S was allocated to P0. And then P1 claimed Q. So Q was allocated to P1. So whenever this process makes a claim and the claim is fulfilled, there is being an allocation edge, right? So what was the next thing that happened? P0 wanted Q. So this P0 is going to send a request edge over here, and similarly P1 wanted S, a request edge here. So if you look at the graph, you still have the same cycle. In fact, the graph is the same as the previous example, but because you have two instances of Q, what will happen is this Q is being given to P1 and this Q is being given to P0, which means what are the resources P1 has at hand now and what are the resources P0 has at hand now. Let me change the color. Okay, so now P1, Q was already allocated. S, it is waiting for. S1, the P1 wants S, but you have only one copy of S, which is with P0. So P1 has only Q. Look at P0. S was already allocated. Q type also it is having now because there's another copy that is being given. So P0 has everything it wants. So P0 will finish working. So ultimately, if you see, there is no deadlock only here. So this Q will be allocated. That's the point I'm trying to make, right? So you have another Q. So this request will be fulfilled and an allocation will be made. So what happens is this also becomes a blue color edge over here. So the cycle gets broken. Both P0 gets whatever it wants. It will do what it needs. Then it will finish. It will give up its claim over Q as well as over S. Now P1 already had Q. Let me just fill in the erased parts. Correct? So P0 is finished with whatever it wanted to do. P1 already had Q. It had requested for S. Now S also is free. So this edge becomes an assignment edge instead. So now this has Q and S both. So it will again do what it wants to do. And then it will also give up the claim. So everything is done. So the idea here is, so this was the case, right? So the idea here is, if you have multiple instances of even one resource, then it is not necessary that a cycle implies a deadlock, right? So what are we talking about in this segment? How do you identify the presence or absence of a deadlock by looking at the RAG? So we saw three conditions. No cycle means no deadlock. If there is a cycle and if every resource has only one instance, there is a deadlock. If there is a cycle and at least one resource has multiple instances, there may or may not be a deadlock. Again, I'm not saying there will not be a deadlock. That depends on how many resources you have, how many instances of each resource, how many processes need. So it is basically case specific. So I'm saying in this last case, there is a cycle and at least one resource type has multiple instances. You cannot simply look at the graph and say this is a deadlock or this is not. You have to sit, you have to work out, you have to see the case specific nuances and tell. But in the other cases, the graph alone is sufficient to tell us whether there is a deadlock or not. So that is that. And we also saw how requests and allocations are made, right? So first a process makes a request, and as soon as that resource is available, the request edge gets converted to an allocation edge. Yeah.